Tajikistan is among the poorest nations in Central Asia. A landlocked country with scarce fossil fuel reserves and a population of just over 10 million people. On paper, it is a nation with limited options. And yet, deep inside a remote mountain valley along the Varksh River, Tajikistan is chasing an ambition that dwarfs its size. The construction of the tallest dam ever attempted by humanity. With a projected cost approaching $8 billion, the Rogun Dam is designed to rise to a staggering height of 335 meters, taller than every dam ever built and even higher than many of the world's skyscrapers. Once completed, it is expected to generate up to 3,600 megawatts of electricity, a level of power comparable to several nuclear reactors operating together. For a country with such limited resources, this raises a crucial question. Why would Tajikistan risk so much on a single project? To understand that decision, we have to look far beyond the present and trace this story back into the past. The vision of the Rogun Dam did not originate in the modern era. Its roots stretch back to the 1960s, when Tajikistan was still a republic within the Soviet Union. During the height of the Cold War, Moscow was aggressively pushing to industrialize its outer regions, particularly Central Asia, through massive state-driven infrastructure projects. Attention soon turned to the Varksh River, one of the most powerful tributaries of the Amu-Darya river system. With its strong flow, steep mountain terrain, and extreme elevation differences, it represented one of the rare locations on Earth capable of supporting an ultra-high dam. In 1976, the Soviet government formally approved the Rogun project. The goal was ambitious and unmistakable: to construct a hydropower facility that would exceed anything built before it, capable of taming the river, producing enormous amounts of electricity, and regulating water supplies across the region. But history had other plans. When the Soviet Union collapsed in 1991, Tajikistan was thrown into chaos. Civil war erupted, the economy collapsed, and the Rogun construction site was abandoned, frozen in time before the vision could be realized. Its economy lay in ruins, and the Rogun site, still little more than an unfinished construction zone, was abandoned to time and decay. More than 20 years would pass before the project would see even a faint possibility of revival. According to project engineers, once completed, the Rogun Dam will rise to a height of roughly 1,100 feet, or about 340 meters, making it the tallest dam ever constructed. The hydropower complex is designed to house 6 massive turbine units with a combined installed capacity of 3,600 megawatts. That level of output is enough to more than double Tajikistan's current electricity generation, creating a substantial energy surplus during the summer season. Rogun is not a traditional concrete gravity dam. Instead, it is engineered as a rock-fill dam with a central clay core. The main body is built from hundreds of millions of tons of rock and gravel, placed and compacted in carefully controlled layers. At its center, the clay core acts as a watertight barrier, while the enormous rock-fill shoulders provide strength, flexibility, and the ability to absorb seismic energy. Behind the dam, the reservoir is designed to hold approximately 13 cubic kilometers of water, placing it among the largest in Central Asia. This vast storage capacity allows for seasonal river regulation, more consistent power generation, and reliable irrigation support for downstream regions. Construction begins with one essential step: diverting the river itself. To build a dam of this scale, the foundation must remain completely dry. At Rogun, this required the excavation of massive diversion tunnels driven deep into the surrounding mountains. 4 tunnels were planned, each extending more than 1 kilometer in length and wide enough to carry enormous volumes of water. 2 of these tunnels were built during the Soviet period and later strengthened and restored, while the remaining 2 were completed after the project was revived. Together, they redirect the Varksh River around the construction zone, allowing work on the main structure to proceed. Only after the river was safely diverted could engineers begin the painstaking process of preparing the dam's foundation. Loose soil, fractured rock, and other unstable materials at the valley floor were first removed to reveal solid, load-bearing bedrock beneath. Any natural cracks within the rock mass were then drilled and sealed using high-pressure grout, a process designed to limit water seepage, bind the rock together, and control underground water movement. Alongside this, an extensive foundation drainage system was installed to relieve uplift pressure beneath the dam, protecting the structure over its entire operational lifespan. At the same time, the surrounding mountain slopes were stabilized using rock bolts, steel mesh, sprayed concrete, and drainage systems, ensuring the valley walls would remain secure long before the dam embankment began to rise. Once both the foundation and slopes met strict safety standards, construction of the Rogun Dam body moved forward in carefully managed stages. Rock and gravel were quarried on site or hauled in from nearby sources, then laid down in thin, uniform layers. Each layer was leveled and compacted with precision to prevent uneven settlement and guarantee long-term structural stability. At the heart of the dam, the clay core was constructed simultaneously, shielded throughout the process to preserve its critical role as a watertight barrier. As the structure grew, engineers maintained constant surveillance. Sensors tracked settlement, internal water pressure, and even the slightest deformation within the dam body. Discharge outlets and control systems were regularly inspected and tested to confirm that every component remained within safe operating limits. In parallel, spillway systems and vertical shafts were carved deep into the surrounding rock through a combination of vertical excavation, structural reinforcement, and phased concrete placement. These hidden channels form the dam's internal circulation network, safely guiding water and managing hydraulic forces during both construction and long-term operation. At the heart of international concern were the countries downstream, whose agriculture relies heavily on water from the Amu-Darya River system. The possibility of Tajikistan controlling such a massive upstream reservoir sparked fears of long-term water security and regional instability. In this sensitive context, the World Bank agreed to participate in the Rogun project, but only after insisting on a series of independent feasibility studies and thorough regional impact assessments. If Rogun represents a high-stakes gamble for a small, resource-limited nation in Central Asia, then the Three Gorges Dam in China provides a striking example of how a single structure can transform a superpower's economy and energy landscape. With its staggering size, the Three Gorges Dam has become the centerpiece of an extensive hydropower network along the Yangtze River. Towering higher than a 60-story building, it holds a reservoir so immense that it has literally reshaped the surrounding valleys and entire communities. At full capacity, this colossal dam can prevent roughly 100 million tons of carbon emissions each year, while regulating the flow of the Yangtze for a region supporting more than 400 million people, an impact far beyond what statistics alone can express. Its most profound and often overlooked role, however, lies in flood control. Before the dam was built, the Yangtze River basin was repeatedly ravaged by catastrophic floods. In 1931, more than 145,000 people died. In 1954, the death toll exceeded 30,000, and by 1998, violent floods destroyed thousands of villages, claimed over 3,000 lives, and inflicted tens of billions of dollars in economic damage. These staggering figures illustrate why China committed to constructing a water shield capable of controlling one of Asia's most volatile and destructive rivers. The real work of building the Three Gorges Dam began in 1994, when engineers set out to create a foundation robust enough to support a concrete leviathan, 2,350 meters long, 181 meters tall, and nearly 115 meters thick at its base, a mass designed to withstand the relentless pressure of billions of tons of water pressing against it every day. To prepare this foundation, tens of thousands of workers excavated an immense volume of earth and rock, carving deep pits down to ancient granite bedrock, hundreds of millions of years old. Each excavation acted as a geological window, revealing the spine of the Three Gorges Valley. Only solid, unbroken rock could bear the weight of a megadam of this magnitude. A vast network of grout holes, stretching for thousands of meters, was drilled into the bedrock and injected with cement slurry. This process bonded the fractured rock into a single, unified block, sealing even the smallest cracks to prevent water seepage. Every section of the foundation was continuously monitored with geotechnical sensors, ensuring no weak points existed. It was this mountain-solid base that would support the immense weight of the structure, enabling the dam to resist the surging forces of the Yangtze River for decades to come. Once the foundation was secured, the massive concrete pouring operation began, flowing through the site like a man-made river of grey stone. Above, the steel arms of 20 tower cranes swung ceaselessly, lifting and placing batch after batch of concrete into over 230 separate blocks spanning the former riverbed. On the ground, mixer trucks and pumping systems operated in perfect synchronization, delivering the heavy mixture precisely where it was needed, as if the entire site breathed in unison. Every layer of concrete had to meet exacting standards for thickness, moisture, and curing time, because even the smallest deviation could weaken the structure. Cooling pipes ran deep into each block's core, stabilizing temperatures and preventing expansion-related cracking. Surrounding geotechnical sensors captured the tiniest shifts, subtle, invisible signals critical to the dam's safety. Day after day, tier by tier, new layers of concrete were poured, until the cumulative volume exceeded 28 million cubic meters, forming a colossal, rock-solid mass ready to rise into the next phases of this engineering marvel. Before construction could advance to higher elevations, engineers faced the project's most formidable challenge, redirecting the entire Yangtze River into a temporary channel while still managing its immense flow. To achieve this, a series of diversion tunnels was carved deep into the mountainside, a critical strategic step in the dam's construction. 3 tunnels, each more than 900 meters long and 18 meters high, were designed to carry the river safely at speeds of up to 11,000 cubic meters per second. Over 1.2 million cubic meters of earth and rock were excavated using precision drilling and mechanical cutting, carefully controlled to prevent vibrations that might compromise the bedrock foundation. Once the river was successfully rerouted through these tunnels, the original riverbed was transformed into a dry work platform, secured by cofferdams and high-capacity pumping stations that maintained stable conditions even during floods or heavy rain. With the river out of the way, the body of the Three Gorges Dam began to rise, layer by layer, lift by lift. Across a sprawling construction site of over 100,000 square meters, steel scaffolding, hydraulic lifts, and mobile gantry cranes formed a dense lattice of machinery, enabling thousands of workers to operate simultaneously at multiple elevations. To ensure structural integrity, the enormous dam was reinforced with over 400,000 tons of steel, meticulously tied across 28 segments stretching along the mountainside. This created a solid metal framework, a skeletal backbone onto which each new layer of concrete was carefully placed, gradually shaping the colossal structure into one of the world's most ambitious engineering feats. Each segment of the dam was lifted in cycles of 1 to 2 meters, forming massive, stepped layers that pressed firmly against the cliffs on either side. Expansion joints were carefully positioned to disperse structural stress, while shear-resistant steel plates secured every connection, ensuring the entire dam acted as a single, unified structure. As the massive wall rose, it gradually tapered toward the crest, narrowing at the top to just 40 meters and reaching its designed height of 185 meters, a critical threshold needed to hold back a reservoir containing nearly 39 billion cubic meters of water. The Rogun Dam is far more than a hydropower facility. For Tajikistan, it is a test of everything the nation has invested in: engineering expertise, financial resources, political resolve, and its long-term survival in a rapidly changing climate. If it succeeds, Rogun has the potential to transform a resource-poor nation into a major energy hub for Central Asia. If it fails, it risks becoming one of the most costly gambles in modern infrastructure history. But the question is not only about height or generating capacity. The deeper challenge lies in whether a single dam can shoulder the destiny of an entire nation. Upstream glaciers are shrinking, downstream communities depend on predictable irrigation, and economic pressures are intensifying. Amid all of this, the project faces the delicate balancing act of capital, construction timelines, and regional trust, a monumental gamble where the stakes could not be higher.